Welcome back. Today we get to the really cool stuff. So I'm excited for today's lesson and the ones coming up. This is where it gets pretty sweet. We've learned a little bit about magnets already and electricity, but how come these are in the same unit? And so today's where we start to discover why these are in the same unit, magnets and electricity. We know that magnets, natural magnets, are just things that have a bunch of domains, and so a magnetic material can have domains that can move around, and if they are all lined up in the same direction, then they're magnetic, okay? But there's a link between that and electricity, and that's pretty sweet. And so in 1820, this guy named Hans Christian Ørsted, he discovered that when proper spelling of when a compass was near a wire with a current in it, the compass started to point in a different direction. It stopped pointing north. And so generally that's not a surprise if there's a magnet nearby, because compasses point towards the south pole of a magnet, right? And so that's not surprising that it would, except for there was no magnet. And so he started looking around and he realized anytime there's a current running through a wire, the compass moves, which means there's a magnetic field around the wire. And then when he turned the electricity off, the magnetic field would go away. And so then he started to experiment with this and think, can I create a magnetic field that would be strong and that I could turn on and off? Now that would be cool. And so that's what he started to discover, and this is called an electromagnet. That's a magnet that is produced by electricity. And so these are super handy. So a couple things we need to know as we get into what he discovered about electricity and magnetism. We're going to talk about current. Electricity is just electrons flowing through a wire. And so that's current. Current is naturally I. I for current. Why? I don't know. It's just how it is. In physics, current is defined by the direction a positive charge will flow, which also doesn't make any sense because electricity is electrons moving. But we talk about if a positive charge would move, that's the direction that current would go. If electricity was protons, even though it's electrons. And that may seem ridiculous, but let's remember, I don't know if you remember in my classroom that lineup of all of the different physicists. When this stuff was discovered, electricity, magnets, electromagnets, they didn't know that electrons existed. This was way too early for that. And so they had no idea that it was electrons that were moving because they didn't even know about the makeup of an atom. So this is insane that they were able to find this at this point. That is why in physics it's a positive charge is the direction that we're following, even though electrons flow. And so he decided that, like I said here, since a compass needle is affected by the field, there must be a magnetic field induced by current. And so we're going to use rules that are called right-hand rules, and this is what Hans Christian Ørsted found. Okay, not Hans Christian Andersen, though do some reading with him. He found rule number 1. This is the first situation he had this straight wire, and he found out that if the current was moving up, like we see here, then B, what is B? Magnetic field. Why? Because. That's how it is. Current is I don't know why. Magnetic field is B, because. It doesn't get simpler than that. So if the current in the wire is going up, the magnetic field is going around that way. Interesting. Okay? How can you know which direction? If it's up, magnetic field is around. And so you see this guy, this is the right hand. If you use your left hand, if you are left-handed, it doesn't matter. These are right-hand rules. Okay? So just get off your high horse if you're left-handed. You know who you are. And start using your right hand for this. Okay? It has to be your right hand. If the current is going up, which way do your fingers curl? Okay? That's the direction that the magnetic field would go. So open up your hand. Put your thumb up. Okay? And start curling your fingers, and you'll see the way that they wrap around that imaginary wire. That's the way the magnetic field wraps around this imaginary wire, okay? And in real life, that's how it works, okay? So some quick examples of this. If current is going left through a wire, so here it was going up, here it was going up, and now we're going to go left through the wire. Left is this way, like that. Now, what direction would the magnetic field be going? Okay, well, use your right hand and stick your thumb. Remember, current is your thumb, your thumb is going to the left, your fingers are wrapping from top to bottom, so it's looking like this. Oops. Something like that. Right? Let's get rid of that. Now that is so hard to read. This is difficult. So that's one way of drawing it. That's a mess. Let's try again. Here's how I want you to draw it. This is I. Okay, the current is going to the left. Now we're going to draw B in red. And it's going to look like this. Here's the big thing. Instead of drawing these lines, we're going to use these. Into the page is an X. X marks the spot you're going in. Out of the page is a dot. Got it? Into the page, X. Out of the page, dot. And so what we can see here is this is going in, this is coming out. So into the page is on top, out of the page on the bottom. Into the page, out of the page. Into the page, out of the page. And that's how it should look. This is good. That's great. And so that we'll just label red is the magnetic field, and we are good. Okay? So that's how you can answer that. And so what he would find is, if you would put a compass here, you would find that the magnetic field would be going into the page, which means like that way. You see which way I'm pointing, into the page, right? Down is another way of saying that. And this, so the compass would be affected just by putting a current through. All right, and so let's say the current of the wire is going into the page. Okay, so there's this wire. I'm going to do that in blue again. It's wire, and it's going X into the page. Okay, it's going into the page. What direction is the magnetic field around the wire? So this is a little bit tricky. The current is going into the page. Put your thumb. That's the current. That's your thumb is going into the page. Which way do your hands wrap around? Do that in red. Is this true? Check. Does it work with your fingers? Are your fingers wrapping around that way? And you're good. B for magnetic field is going around, and we call this clockwise. You can't just look back at the clock in the classroom. You might not even have a clock like this in your house, but maybe, hopefully you do. Go watch it for an hour today. There's some homework. And figure out what clockwise is. Okay, that was rule number 1. But then he realized that this was super weak. Okay, the magnetic field is super weak. It could hardly even affect compass. And so he's like, how could I enhance this? And so what he did is he started coiling wire around. And as you coil it, the magnetic field starts to build on each other, and it gets stronger. And so this is super important. Okay? And so once again, there's still just 2 things. There is the current and the magnetic field. I for current, B for magnetic field. But this time, notice the current is now your fingers and the magnetic field is your thumb. We're moving on to a second rule. Okay, second rule. This is when it is coiled around. Okay? And this is different than this. This is when the wire is straight, then the wire is your thumb. And here, when the wire is coiled, it acts differently. And the current is your fingers that coil, right? And the magnetic field is now your thumb. Okay? And so what happens is, if the current is going like this, as you can see, it's going up and around and then down the end. So we're looking at this picture here. Then look how your hand goes, and your thumb is pointing in this direction, which means inside we've got a magnetic field. Let's do, the current is in blue going around like this and down here. Okay, we've got a magnetic field that is going through this way, which means on the inside it's going through, and it's going out here down and out and around and in. Oh my goodness, this looks a lot like what we did the other day, which is, this is a bar magnet. We actually created, by putting electricity in here, we created a bar magnet. Inside, the magnetic field is going through the direction of your thumb, and then on the outside, it's going around like a bar magnet. This becomes the North Pole, this becomes the South Pole. Okay, so some quick examples. If current is going counterclockwise through the wire, what direction is the magnetic field within the coil? So now this is a coil, so we're using right-hand rule number 2. Okay, so get your hands out and start thinking. Just be careful. Current is going counterclockwise. Counterclockwise means we start at 12 and we go backwards, right? This is the direction of the current. I should do that in blue, just to be consistent. The current is going this way. That's I. Okay? What direction is the magnetic field? Use your right hand. I is circular. This time, I is your fingers. Okay? And so your fingers now coil that way, and which direction is your thumb pointing? It's pointing right at your face, right? It's pointing out of the page. And so we put a circle with an X. Nope, that's wrong. That's into the page. A circle with a dot. And that is the magnetic field. And that's your answer. That's how you write your answer. Isn't that? It looks ridiculous. Some sort of hieroglyphic, but it's correct, okay? Number 2, the magnetic field within the coil is moving from east to west. Now this is a coil or something like that, and the magnetic field within it, that's red, is moving from east to west. It's moving this way. Okay? Now what is the direction of the current? Excuse me. Flu. What is the direction of the current in the coil? So if the magnetic field is going from east to west, that's red, that's their thumb now. What is the direction of the current? That must be, look at the way your fingers curl. They go from on top, they're going into the page up top, and on the bottom they're coming out of the page. That's your I. And so then you've got the answer. Okay? So this is what I'm looking for. This blue stuff there. Your answer is there and there. I need both. It's going into the page and out of the page. And since the magnetic field is going through that way. That's interesting stuff. Okay? And so what this means is if you put the current like that, you'll get a magnetic field going out here and you'll get this bar magnet. So what does this look like? Let's draw the magnetic field around a solenoid if the current is moving from left to right. Okay, so what that looks like is the current is moving from left, that is this side, and it's moving in and going out there. And you can see this is going down and up. So this is out of the page and into the page, right? And so then let's put our hands that way, into the page, out of the page, and we see that the magnetic field going through and then out, in there, around the back, just like that. And that's what it should look like. So we've got here a North Pole and a South Pole. That's it. That's what we're looking for. So for today, I've just given you a practice paper. It's not for marks, but I would encourage you to hand it in just to get some feedback. I will give you feedback on that if you hand it in. All right, and that's it for today. Have a great weekend.